Okay, so we've got three scenarios where we can actually calculate the magnetic field, and it turns out that a moving charge in an external magnetic field experiences a force. So this is the second part of the chapter. Moving charges experience force. So whether it's an individual charge that's moving or it's a collection of charges moving, like say in a wire, they will experience a force. Okay, good. So individual particles moving are currents in wires. Okay, so if you supply current through a wire in an external magnetic field, it will experience a force. Okay, that's what a motor actually is. So you supply current, it's in a magnetic field, and you can get a loop to move around. Okay, so the charge has to be moving. So here's a magnetic field. In this picture, blue is the magnetic field, and it's pointing in the direction that you see. It's not moving, so there's no force. If there's a charge in a magnetic field but the charge is not moving, it does not experience a force. If it's moving in the same direction or the opposite direction of the magnetic field, there's no force. So if V and B are lined up, or if they are 180 from each other, there's no force. Okay, so V has to have some angle between itself and B for there to be a force. Okay, and you can see from these pictures, I'll just say this is 1, 2, and 3. There's an angle between V and B, and then the force is perpendicular to the plane made by V and B. So notice too in 1, 2, and 3, the force is the largest in number 3. So when V and B are perpendicular to each other, that's when the force is the greatest. When V and B are lined up with each other, the force is 0. And then in between, it gets larger and larger as the angle gets bigger and bigger. Okay? So I mentioned in class, you've got to get used to thinking in 3 dimensions. This is what I was talking about. So the force is always going to be perpendicular to V and B. If there's a force, if you have some angle between V and B, the force is always perpendicular to that plane. Okay, and this is the basis of a motor, an electric motor. So the magnetic force is different than the electrical force. It's always perpendicular to the direction that you're moving. So magnetic forces never make anything speed up or slow down. They just make them change directions. Okay? So the particle's got to be moving. That's a difference also. If it's stationary, there is no magnetic force, even though there's a magnetic field. Okay. So pretty interesting stuff. We determine the correct direction of the force by using the second right-hand rule. So if there's a positive charge, this would be the direction of the force. And we'll see how we figure that out in just a minute. Now, if this charge was negative, the force would be downward, but it's up because it's a positive charge. Let's see why that is. Okay, so this is the second right-hand rule. You've got to put your hand like this, and then line up V with your thumb, B with your pointer finger, and then the rest of your fingers are the direction of the force. So if you forget which is which, here's your hand. You could write a little V, a little B, and then F for the force. Okay? And that'll give you the direction of the force if it's a positive charge. If it's a negative charge, you just have to rotate it around. The force is just the opposite direction. That's the easiest way to say it. A negative charge, your left hand actually works, but that's pretty advanced. Okay, so line up your thumb with V, your pointer finger with B, and then the rest of your fingers are the direction of the force. Okay, good. So positive charge, there's the force, just like we said. So if you line those up, you would see V, the way I'm looking at it, is to the right, B is this way, so the force would be up. Okay, we'll get some more practice when we meet again in class too with this. Okay, so here's the magnitude of the force. QVB, and then sine of the angle between V and B. So this is the angle between V and B. This is alpha. Okay, so the force is a maximum when the angle is 90 degrees. Sine of 90 is 1. Sine of anything other than 90 is smaller than 1. And when the angle was 0 or 180, then the sign of 0 is 0, and there is no force. So this just gives you the magnitude of the force. You have to use the right-hand rule, the second right-hand rule, to get the direction of the force. Okay, so let's see what's going on here. Here's a bar magnet, and here's a charge that's moving in the direction that you see. So you've got to line things up. So V, so take your thumb and put your thumb in the direction of V. Now B, if you're looking at it, goes from right to left. So V, magnetic field is right to left. The force is out of the page. It's coming right out at you. So if there's a charge moving there, the force would be out of the page. So out of the screen, as it says here. Okay, so line those up and you should get the same thing. So the velocity and the magnetic field are perpendicular, so the magnitude of the magnetic field becomes this when they're completely perpendicular to each other. So that's when the force is a maximum. Okay, good. So again, determining the magnetic force on a moving charge. You've got to line these things up with each other. So this is a good picture of that. Thumb in the direction of that it's moving, that's where V is. Put your pointer finger in the direction of the magnetic field, B, and then your rest of your fingers give you the direction of the force. You've got to line them up perpendicular to each other. Okay? Now a negative charge, you do the same thing, you line them up with each other. So V is this way, B is this way, the force would be down, but it's a negative charge, so the force is up. So for negative charge, do it the way we've done it, but if it's a negative charge, the force is just the opposite direction. Okay? Let's take a look at this one. The diagram shows a top view of an electron beam passing between magnets. So we know the magnetic field direction is this way, from north to south. So this is the direction of B. And it's moving down. So you've got to try to line these things up with each other. Sometimes you've got to contort your fingers a little bit. So V is the direction that it's moving. So the thumb is pointing down. B is the direction of the magnetic field. So I've got to rotate my hand around. It's hard to do this because I'm trying to do it so you can see it. So V is down. B is to my right. The force would be out at me, but it's a negative charge, so the force is into the page. Okay, good. So again, line them all up, and then with this one, it's a negative charge, so whatever you get for the force, it's the opposite of that. Okay, so electron is moving to the right, so I already see that B is up. So electron is moving that way. The magnetic field is up, so the force would be out of the page, but it's a negative charge, so the force is actually into the page. Okay, and you can see here from this from the picture. Okay, that's a synopsis of what I've just said. Okay, good. So line everything up. It takes a little bit of practice. Sometimes you put your hand one way, and then you realize, oh, I can't bend my hand that direction. Like you don't take these fingers and try to bend them this way. It's always like this. Okay, and then in class we'll take a look at these 22 and 23. Okay, so paths of charged particles in magnetic fields. The force is always going to be perpendicular to the velocity. So all this can do is change the direction that the particle is moving. It's not going to change the speed. No part of the force is opposing the way it's moving or making it speed up. So it doesn't change the kinetic energy at all. It just makes it change directions. They can go in a circle, actually, as you see here. So remember from Circular Motion, Chapter 6, whenever anything goes in a circle, there has to be a force towards the center. So in this picture, this charged particle is moving counterclockwise. So here's the direction of V. It's moving in a circle, so there has to be a force towards the center. And you can line all these things up. The magnetic field is into the page. That's what the X's represent. So you have to, again, think about things in 3 dimensions and try to line these up. Okay, so V is the direction that it's moving. B is into the page, so then the force is towards the center. So they all line up with each other. Okay, excellent. So now if you go in a circle, if you remember back from Physics 220, we did something like the net force is MA. It's just when you're going in a circle, the A is a special kind of A, radial acceleration, and that's equal to mv squared over r. And then, you know, what is the actual force? You would put that over here. Well, if we're talking about a magnetic field changing the direction, then this would be QVB. And that's the magnitude of the charge. What you can also use for circular motion, if you remember, because if you go in a circle, a constant speed, the speed is 2 pi r, the distance around a circle, divided by the period. Okay, so we're taking what we learned in chapter 6, circular motion. It's just now we have a new force we could put into the fold here, this magnetic force, QVB. Okay, good. So if you've seen the northern lights or southern lights, the borealis, you have experienced this. The Earth's magnetic field makes the particles go in a circle. They're accelerating, they give off light, and that's what you see. Okay, you can do a little bit of algebra to the previous equations. Let's see, we had mv squared over r is equal to QVB. There's a V on both sides, so this V and this V cancel out. So you have mv over r is equal to QB. And then you could, what's being done here is just solving for r. So mv over QB. That would give you the radius of the circle. So this is the northern lights. This is also some mass spectrometers work on this idea. Now, if you notice, if a particle comes in with a certain speed, and you can control that using electric fields, the radius of the circle it goes through, if you knew the charge and the magnetic field strength, would just depend on the mass. So more massive particles would have larger radii that they travel. So and you can figure out what the radius should be and try to measure whatever you're looking for. So for example, say you're trying to measure how much carbon-14 you have, you would set a sensor at the radius that you would expect for carbon-14, and charged particles come in, they hit the sensor, it registers as current, and you can figure out how many of the particles you have in doing that. So it's one sort of mass spectrometer using magnetic fields. Okay, so we need the part of the velocity that's actually perpendicular to the magnetic field. So if the blue here is the magnetic field, this is the part that's actually perpendicular. That's the part that would make it go in a circle. So this would actually, this particle would actually kind of spiral. It would go in a circle, but it's already moving, you know, up on your screen. So it would continue to move up. This parallel part would make it move this way, but this part, the perpendicular part, would make it spiral. Okay, so it would kind of loop around. So here's a top view. Here's the perpendicular part making us go in a circle, and then it's already moving in another direction, so we would have a nice helical path. That's more of what the northern lights look like. Okay, and then there you see the spirals. Okay. The circular part coming from the perpendicular part of the speed, the parallel part of the speed making it go this way. All right, pretty cool. And then there you can see a better picture of it. So these particles come from the sun, they get intertwined in the Earth's magnetic field and spiral to the poles. It's a good thing that they actually do, because if you get hit by charged particles, it could be very bad. It could drive our, astronauts actually report seeing flashes of light in their eyes if they're away from the Earth's magnetic field. They're being hit by these charged particles. I mean, they shield for it. NASA and other agencies shield for that, but it's not as good as having the Earth's magnetic field shielding all these particles from hitting you. Okay, good. So let's take a look at this. The direction of the magnetic force on the electron. Okay, so the electron's moving one way, the magnetic field is exactly the opposite way, so there's 180 between V and B, so there's not going to be any force. Okay, magnetic force is 0 here. There's no part of the velocity that's perpendicular to the magnetic field. Okay, so this is a neat way of actually measuring blood flow rates. How fast is it moving? So if you connect a north and a south battery, charged particles in the blood, it doesn't have to be blood, but I think maybe this example was meant to be that. This is a way of measuring blood flow in an artery without actually cutting into the artery. Anyway, so positive and negative ions flow to the right, and when they do, there's going to be a force on the ions that drive them to one side or the other of the whatever it's flowing through, and then it's going to set up a voltage, and you could measure the voltage. So here's an end view of this. So an end view shows that the magnetic force on the positive ions is to the right, and the negative ions is to the left. So positive ions are pushed this way, negative ions are pushed that way, and then you get a potential difference between the sides, and you could measure the potential difference, and that's proportional to how fast the charges are moving. Okay.